Hi, this is Jianqiao. Today I'm presenting MTU, the Multifunction Tree Unit for accelerating zero-knot proofs. We focused on the balanced binary tree, which is a key computation kernel across many ZKP protocols, from SumCheck to Merkle trees. In this work, we systematically evaluate these tree-based workloads and introduce a hybrid traversal method, as shown in this animation. It improves the parallelism and scalability while greatly reduce the memory traffic. We then apply the hybrid traversal to our hardware design and evaluate its performance. With hybrid traversal, MTU achieves over 1400x speedup compared to the CPU. So before diving in, let's first record what a zero-knot proof really means. Traditionally, if Alice wants to watch a movie, she shows a full ID to prove that she is qualified. The theater can check her age, but also learns everything else about her. With ZKP, Alice can generate a small cryptography proof instead. The theater can still do the age verification, but it learns nothing about her actual age or any personal details. Today, ZKP are not just theory. They have been deployed. For example, Google uses ZKP to build their private age verification pipeline. Another example is ZKML. The server can prove that they use a claimed model for the user's inference without leaking the model's secret weight. A typical ZKP protocol has two parties, a prover and a verifier. In this talk, we focus on the prover side because generating a proof is usually the most expensive part. You may have heard of different protocols like GKR, Hyperplunk, Spartan, Orion, or building blocks like SumCheck and NTT. These are all widely studied in the hardware community. Across these protocols, we often see a common pattern, that is the binary tree style computation that shows up in many prover workloads, such as build multilinear extension, MLE evaluation, Merkle trees, or the product trees. But this pattern doesn't receive much attention. Our goal is to fill out this gap. Let's start with the build MLE workload. Zero-knot proofs is an intersection of math and computer science. Here we have a chunk of data that's stored in a lookup table format. In the ZKP, people prefer to represent this data as a polynomial coefficients or evaluations. Specifically, there is something called the Multilinear Extension or MLE. A polynomial is multilinear means that each variable's degree is at most 1. So the table on the right corresponds to the polynomial like this one. When we evaluate this polynomial at a certain point, the results match the data entries. So it is just another format to store the same information. For example, when we plug in a specific value like 0, 0, and 1, the evaluation gives us the values that correspond to the lookup table. The term extension means that these polynomials can accept not just 0 and 1 like here, but they can also accept other values. In many ZKP protocols, especially SumCheck, the build MLE is very common. That is, we need to evaluate an EQ polynomial for every binary point. This formula looks complicated, but conceptually it is equivalent to build this table involving some random R's. Each row in the table corresponds to a combination of R, and for each of the 2 to the mu rows, we perform mu modulus multiplication. This direct brute force method will be expensive. To make it faster, we can use a binary tree structure. The idea is to plug in the new R value layer by layer to get the result table. Another workload is the MLE evaluation. It is an inverse of the previous slide. Given the polynomial in its lookup table form, we want to evaluate it at some random point R. We need to plug in these R's and compute the inverse of the binary tree for the result. Another common workload is the Merkle tree commitment. Here, the operation is to hash them together. The product tree follows the same pattern, except that it changed the hash with modular multiplication to compute the products. The main challenge of these workloads is the scale. These trees can have large data bitwidth and millions of elements, so we need an efficient approach to handle them. So we'll use build-MLE as an example to go through all those approaches. We are not using this small example, but rather a larger one like this. The breadth-first or level-order traversal is the most straightforward way to implement the tree in the hardware. Since all nodes at the same level are independent, we can process them in parallel, and it can also have a nice property that the output are continuous, with the results producing every cycle. However, the downside is the memory bound. Each intermediate level of the tree must be written to the off-chip memory because they are too large, and then read them back again. This data movement consumes bandwidth, and eventually the system performance depends on the DRAM bandwidth. The depth-first traversal is another way. Unlike BFS, it walks down each branch before moving to the next, so naturally it limits the parallelism because of the dependency. The advantage is that the intermediate results are used right away, so we save the bandwidth and the storage. A solution to improve the parallelism is to divide into multiple subtrees, but the output will become discontinuous with a gap between each of the subtrees. That makes it harder to keep the downstream modules busy. For example, a downstream module that expects a steady stream coming out, but the DFS gap will make them mismatch, so it reduces the overall throughputs. To summary, with breadth-first traversal, we can expose a lot of parallelism because many PEs can work on the same level at once. But the downside is the bandwidth because the intermediate level has to move back and forth to the off-chip memory, so it quickly becomes memory bound. While with depth-first traversal, it minimizes the memory traffic because it keeps the intermediate data local, but the data dependency limits the parallel PEs. In other words, if there is only one PE, then the DFS would be fine. So, to combine the strengths of both BFS and the DFS, we designed a hardware-friendly hybrid traversal. In the lower level, we follow the BFS using just one PE. These give us the memory efficiency advantage, while avoiding the discontinuous output problem. And then, for the output level PE, we switch to BFS to exploit parallelism. In this way, we achieve both memory efficiency and high throughput in one unified design. The first takeaway in our hybrid traversal is to control the generation rate. The DFS PE produces one item per cycle, and that output immediately passes into the BFS PE, which expands into two results per cycle. You can think of it like a domino effect. The DFS PE keeps pushing the BFS PE to maintain steady output. When we connect more BFS PEs, we can produce even more output per cycle. The second takeaway is keeping all intermediate values inside the pipeline instead of sending them off-chip. This again makes the design more memory efficient and let us scale the throughput just by adding more end-level PEs. Here is an example how to map the build-MLE workload to our MTU architecture. First, the DFS PE takes some cycles to calculate the upper level of the tree, and then it maintains the generation rate to feed the input for the BFS PE group. And at the end, they will be used to keep producing the result level elements. In this way, it reduces the bandwidth overhead because those inputs are not fetched from the memory. They came from the BFS PE directly. Here on the left is the detailed MTU architecture. It supports both the forward and inverse binary tree computations. By applying our hybrid traversal, MTU significantly reduces the memory cost while maintaining the high performance. Finally, here is a quick look at our results. We can see that on the CPU, different traversal methods make small difference. That is because on CPUs, the bottlenecks comes from the modulus and hash computation, not the data traversal itself. The CPU is already busy doing the arithmetic. For hardware, MTU applies hybrid traversal. We also model the BFS and DFS with the same number of PEs for comparison. In low bandwidth setting, BFS performs worse because it has to move large intermediate data off-chip. The bandwidth significantly limits its performance. Given larger bandwidth situation, MTU scales more efficiently as we add more PEs because the hybrid traversal uses bandwidth more efficiently to sustain high parallel utilization. We can see here that the latency between DFS and MTU looks quite similar. But remember, DFS actually runs multiple discontinuous subtrees in parallel, which requires extra data rearrangement and additional matching logic with the upstream or the downstream. Those overheads are not reflected in this figure. So in practice, MTU achieves better performance scaling and memory utilization while keeping outputs continuous and efficiently pipelined. The MTU design is compact and flexible, making it easy to integrate into large chips to build a full ZKP SoC, or even as a chiplet to enhance the reuse. To wrap up, I conclude MTU, the Multifunction Tree Unit, a hardware-friendly design that uses hybrid traversal to improve memory efficiency. MTU can handle different types of binary trees, all within a unified architecture. Thank you very much.